Alright folks, let's talk about internal loads today. So, previously we have been dealing with determining external forces acting on a structure. So, taking your distributed loads and turning them into equivalent concentrated loads, figuring out what sort of reactions those are going to cause at supports, so on and so forth. We're figuring out how forces that hold the structures together work. What sort of tension or compression you're going to have in members of a truss, etc., etc. So we're going to start looking inwards. So we're looking at internal forces. So those are stuff that is developed within a member, and those are what hold the member together and transfer loads from that member to external bodies, such as supports, or other parts of the structure. So a internal load is what gets the tension from one end of a two-force member to the other end of a two-force member. So generally speaking, we're talking a few types here. We're talking tension or compression, we're talking shear, and we're talking bending. A little bit more detail on those. So yeah, types of loads, external loads, internal loads. External loads are acting on the structure. Got the two types, external forces and body forces. So external forces are caused by direct contact between physical bodies. Could be because of something that's touching it, could be something based upon the environment it's operating in. So for example, a submarine is operating at a particular depth. It's going to have an external load applied upon it by the water pressure, the hydrostatic pressure of the ocean water pushing on it. So again, those water molecules are indeed physical bodies. They may not be solids, but they are certainly physical bodies. Reaction forces, so various components interacting with one another, can also be considered external forces. Come on, there we go. Body forces, those act remotely throughout the volume of a body. So again, we generally take them and turn them into some sort of resultant. The most obvious body force that comes up is good old gravity. There are others. Magnetism acts remotely throughout the volume of a body. Again, not necessarily equally at all points throughout the volume of a body. Electrostatic forces could do the same thing, so on and so forth. And then we got our internal loads. So again, those are generated in the structure, generally as a result of external loads, and I'll digress a little bit. Usually we can make the assumption that if a structure is just sitting there doing nothing, the internal loads would be zero if it was in a zero gravity state. Now again, when we talk external loads, the weight of the object itself is one of them. That having been said, there are going to be some situations where some sort of residual loads exist within a structure, just based upon its configuration, based upon how it's set up, independent of any external loads that are applied. And sometimes these residual loads are helpful, and sometimes they're harmful. and sometimes it can be difficult to determine whether or not that's the case or not. But that's a bit beyond the scope of this course. You're going to start getting into some of that next year. So so the internal loads are generally the result of the external loads, and they allow you to figure out kind of how the different external loads that are applied make their way through the structure. So again, if we have gravity pulling down on this water bottle here, it's going to be distributed in a certain manner such that there's a certain load path that makes its way up to my fingers here. So those would be internal loads that determine what sort of reaction is occurring at my fingers. So one of the keys here is equilibrium of sections. We describe internal loads by taking imaginary slices of the structure and just figuring out what sort of forces would have to be applied to the face that we just cut in order to keep that structure, that half of the structure, in equilibrium. So if a body is in equilibrium and you cut it and apply certain forces to that cut, if those forces are the same as the internal forces that would be generated based upon its loading conditions, then that body, then those forces describe the internal forces of that body under its loading condition. So as long as everything's in equilibrium, then basically we're describing kind of what's going on inside the component. Because obviously we can't just go and look at what's going on inside the component because we can't see through metal. So generally speaking, you can take whatever forces are acting on a face, and you can replace it with some sort of force and some sort of moment, a force-moment couple. That having been said, oftentimes we will go and break that up into different components that when combined have the resultant that we started off with here. But those different components that we have kind of help us draw useful conclusions about what's going on inside the member in question. So when we're talking the force part of the forced couple system, we generally break the force up into two types. So we've got a normal or an axial force. So that's the portion of the force that is acting perpendicular to the cross-section plane. So it's coming straight out of that face that we cut. And then we got shear force. So shear force is any portion of the force that's acting parallel. It's acting parallel to the plane. So, and again, when we take the shear force and we take the normal force and combine them together, then that resultant needs to be whatever force would help to keep this body in equilibrium. So this force here needs to be the equal and opposite to the resultant of all these forces applied to the other side. So oftentimes we not only worry about not the shear, but we worry about we might break the shear up into not just in this direction. We might also break it up into an X component and a Z component. a y component and a z component. I'm going to say that because typically speaking, we often reserve the x direction for the axial. Again, it does kind of depend upon what components you're looking at, but especially, yeah, usually the x direction is going to be what we define the axial as. So it's yeah. So those are the force portion. We also break the couple of the force couple system up. So the torsional moment, or torque, that's the portion of the force couple system that's oriented perpendicular to the cross-section plane. Or to put it another way, it is the twisting motion that is acting about the axis sticking out of that plane. So, if we have if we have this pen here and we slice it this way, then the torsional moment would be what sort of force is acting about the axis that is sticking out of the slice. So about this way. It's a twisting motion. You're twisting. And then the bending moment, so the portion of the couple oriented parallel to the cross-section plane. So we're not doing this for those. We're trying to bend it. We're causing a moment that does this. We're causing flexion. We're causing this thing to bend. It's not a moment about this axis. It's a moment about this axis. So we're bending this way or that way, or possibly this way or that way. Because like the shear force, we often also break the bending moment up into portions that are about the y or the z axis as well. So it's torsional moment is only has one possible component to it because it is defined by the face that's cut. The directionality there is defined by that. You can't break that up anymore. It's coming straight out. Same with the normal force. Whereas the bending moment, you can break it up into different subcomponents in this direction and this direction, or what have you. If we're just looking at a 2D structure, then it gets a bit simpler. So we're generally speaking dealing with shear force, bending, and normal force. So again, normal force coming straight out. Although in this instance, based upon the diagram that was given, the resultant force would actually be this direction. But anyways, that's, again, if you go to solve for your normal force, you just end up with a negative value. That's okay. Got the bending moment, again, about this way. And then we got our shear force. So if you're talking a strictly 2D, then you don't have any torque, because torque would require some sort of application of a torque would require the application of some sort of force that has an offset in the z direction. So if we moved over this way and then applied a force down this way, then that would cause a torque. But if it's strictly 2D, then we can't really be doing that. So the internal forces in two force members, we certainly touched up on this. It's in equilibrium with the forces applied being equal. So if we take a cut here, then and we break this bar up into AC and CB, instead of AB, well then, essentially, when we take this slice, what's left here needs to be the same as here. So we just, this force can be basically, this force here just needs to go ahead and get moved right there. Problem solved. So the internal forces need to be equivalent to the two forces that are applied on either end, and that's all there is for a straight two-force member. As long as this thing's straight, then the forces, the internal loads between the points where the forces are applied on that two-force member stays the same throughout. It's all axial. All axial, all normal, no shear, no bending. If we have multi-force members, so typically speaking, you need a force couple system when you're taking a slice. You need a force couple system. You're generally speaking going to end up with some sort of combination of axial and shear and a moment in order to maintain your equilibrium. I will point out there are some loading conditions where this won't be the case. If we have a multi-force member that looks like this, and we got it's supported here, and it's got a weight that's applied here and a weight that's applied here. It's not a two-force member anymore, right? It's got three forces that are applied to it. And it's not pinned at the end, so it doesn't have that freedom to rotate that a two-force member has. But at the same time, if those are the only forces that are applied, then we're only going to be generating axial or normal loads. They'll just change as they vary. So you don't always have to have a force couple system, but you always got to be prepared for that to be the case. And in some instances, or actually most of the time, you're going to be getting situations where the structure will have locations on it. All right, there'll be parts where you could take a slice and it will have zero internal moment. And it might have a zero internal force. That doesn't mean that just because you find a spot where there's zero internal moment, doesn't mean that you can assume that there's zero internal moment throughout the structure. Those things vary based upon the loading conditions and the position. So, taking a slice at one point tells you what the internal load is at that point. It doesn't necessarily tell you what's going on everywhere else. And non-straight two-force members. So again, if we have this thing here and it's pinned to something else, it's still a two-force member. A two-force member is defined by its loading conditions. So if it is just pinned at two ends, it's a two-force member, no matter what. That having been said, because this thing isn't straight, if we take a slice here at D and break this up into these two components, then essentially we're not going to have just axial forces that are able to keep this thing in equilibrium, because it's not straight. Because the point that we're looking at is no longer in a, it's no longer completely in line with the line of action of the forces. So if we take this slice up here, in order to basically have this thing be in equilibrium, we're going to have some sort of combination of axial force and shear force, and these two these two together are going to have a resultant that's equal to P here. Or F plus V needs to be equal to minus P. And then we're going to have a moment here in order to account for the fact that otherwise this here and this here forms a force moment couple. So if we don't have an internal moment applied, then that little thing is going to start spinning out of control, and obviously that isn't actually happening. So we just need to be able to measure what that internal moment is that's preventing that thing from spinning out of control. So yeah, axial force, again, tension or compression. We're pushing on it or we're pulling on it. The sign convention, and everyone uses this sign convention. If you ever use a different sign, the opposite sign convention, you are wrong. The sign convention is that a positive stress and a positive axial force is tension, and a negative axial force is compression. So again, applies to any normal force on a cross section, and yeah, in a straight two-force member, that is the only force that you will ever see. So we'll do an example here. So I'm just going to draw a quick diagram here. So got our position X, and we have our force actually here, and I'm going to call it N of X, the normal force as a function of X. So we got this load here, this 5 kilonewton load. Now if we take a slice right here, then in order to maintain equilibrium, well, we got 5 kilonewtons on this side, so we need 5 kilonewtons on this side. So again, from here to here, that's just, that's stretching, that's tension. So we can go ahead and figure out what, we can go ahead and say, hey, that is a positive 5 kilonewton axial force, normal force. And then moving along, so we that's going to be constant until we hit past this 8 kilonewton force here. So if we take a little slice right here, and we look at the free body diagram of that thing, here I'm going to switch back. So we got 5 kilonewtons, 8 kilonewtons here, and we've got at this face some sort of force. So I'm gonna draw it on here as our N. I'm gonna draw it coming out of the face that we took the slice on, because again, if this was tensile, then if we took a little slice here, then we'd have N and N, and that would be tensile. So we assume that the N is tensile, and then we solve for it. So just taking the sum of our forces in the x direction, we'll have 8 minus 5 plus n. So when we solve for n, it's going to be n is equal to minus 8 plus 5, so n is going to be minus 3. So on this side of the cut, that thing is actually going down to a -3 kilonewton axial force. So we got our 5 here. That drops down to -3. And that continues on until we hit this one here. So again, we just do the same thing. Not sure why those lines aren't erasing. Oh well. Okay, and then we'll just do the same thing here. Take a slice on this end and see what happens. So again, we'll draw our N. We got a 4, got an 8, and we got the 5. 5, 8, 4. So taking the sum, N plus 8 plus 4 minus 5 is equal to 0. So solving for N, -12 plus 5 gives us 7. -7. So we're dropping down again. So this drops here, down. All right, so I guess I'll label this 5, and then we got -3, and then we got -7 over here. So we're staying at -7, and we stay at -7 until we get to the end here. And yeah, that's the end. So you'll note, we changed the value of the axial force diagram when we hit our point loads, and not surprisingly, the amount that it changes is equal to the amount of the point load. So when we add the when we add a positive 8 kilonewton axial load here, that drops us down 8. Drops us down another 4. And then from here, we're already at -7. Then we hit a -7 kilonewton force applied to our free body diagram, and then it jumps us back up to 0. So yeah, that's kind of how that works for at least axial loads.